Hi students. Well, for the downtown students, welcome to week 2 of coronavirus craziness. For Southwest students, this is our first round. There is you guys have asked a bucket load of questions and a bucket load of good questions. My goal is to keep this to under half an hour, 45 minutes at the max, because I wouldn't want to sit here and watch myself on video for half an hour, 45 minutes. So I feel sorry for you for having to do it, but this is what we're stuck with. So I will try to get to as many of these different questions as possible. I've tried to pick things that lots of people asked so that I don't have to, to answer as many people's questions in the time that we have here. Okay, so first of all, a general idea about the expanding universe, all right, and the playground ball, okay? The playground ball is an outstanding example of the expansion of the universe. Now, why is this? Well, because if you put stickers all over this ball and you inflate the ball, the stickers themselves do not expand. They're carried on the rubber of the ball. There is no center to the expansion. Okay, so multiple students asked, well, where's the center of this expansion? And the answer to that question is there's not a center to the expansion. Okay, I'll show a demonstration of this up on the screen in a little bit. But if you imagine having stickers stuck all over this ball and then gradually inflating it up, what is expanding? The rubber is expanding. The stickers don't expand. Okay, so in the and there's no center to be found because the center, the rubber, is like the space of the universe. So the space of the universe is expanding. The galaxies are like the stickers. Okay, the stickers would be galaxies. They don't expand. They're simply carried along in the expansion of this rubber, the space, okay? And then if you were a little creature and you could travel from sticker to sticker, from galaxy to galaxy on the surface of this ball, looking for the center, you would never find it. Because let's say you're here and you say, well, I want to head this way, looking for the center of the expansion. Well, you would go around and around and around and around and around, and then you would eventually come back to where you are. Okay, and you would not find the center. And every creature on every little sticker on this ball would do the same thing. And none of them could find the center because the center isn't on the rubber surface of the ball. The center is in the middle of the ball, which is not part of the surface. So if we think of the expansion of the universe, there isn't a center because that concept would be, in a sense, outside of the universe itself, okay, outside of our normal conceptions of it. Just like the little creatures that walked around on the surface here don't see a real expansion. Oh, don't see a real center, sorry. Now, what does this mean? Okay, so somebody asked, is there any new material that's created in the expansion? No. Okay, you have the Big Bang, but the expansion of the universe that follows that, whatever material is there at the beginning is there now and will be. Okay, there's not new material being made. Okay, it's the space that's expanding. The galaxies are moving away from each other. Okay, the universe then is getting less dense. So someone asked the question, could a galaxy go so far that it wouldn't be visible? And the answer to that question is yes, okay, it could. In fact, we think that in the far future, astronomers would not be able to see other galaxies because they would have moved out so distant. So the universe is spreading out, okay? There's not new galaxies, new material, new planets, new anything being made. So you aren't expanding. The distance between the Earth and the Moon isn't expanding. The distance between the Earth and the Sun isn't expanding. The galaxy that we're in, the Sun from other stars, that's not expanding. I mean, you can have, Earth is in an orbit around the Sun that's slightly elliptical, so sometimes it's getting closer and sometimes it's getting further away. But that's not what we mean, okay? We mean, this broader idea of expansion. Things that are gravitationally tied together or held together by their own material strength are not expanding. But the space between galaxies, or specifically the space between little galaxy groups, remember that the Milky Way has some friends, the Andromeda Galaxy, the Large and Small Magellanic Clouds, a couple other things that all kind of hang together. They're actually all gravitationally tied into sort of one system. Other systems, other galaxies are what are expanding away from us, okay? So only space, okay? Galaxies themselves are not expanding. As one student put it very well, said only distance changes, nothing else, right? Is what she was asking. Yes, only the distance between the galaxies change, nothing else. No new material, no expansion of stuff inside the galaxies or anything like that. No new things are created, okay? We don't get new things made. The universe is expanding, thinning out, so to speak, as everything spreads apart. The universe is undergoing social distancing, major social distancing over its entire lifetime. What is making the expansion take place? That would be the energy from the Big Bang that initially sent everything outward, and then, of course, the dark energy that is continuing to drive the expansion. So now let me show this idea of no particular center to the expansion. I'll pause my video for a minute. Okay, so what I have here is I have put a whole bunch of little circles up on the screen behind me, and they represent, say, galaxies, okay? And now I'm going to select the whole lot of them here, and I'm going to copy them and paste that copy back on top. Now, as long as the copy is the same size, not expanded, I can put them right on top of each other, like that, okay? Now, what happens, though, if I go and I make the copy expand? So I just enlarge the copy. Now you'll find that every one, if I choose here, that one right there, up there. I look at that one. Notice how all the others seem to move away from it, okay? Now, you say, oh, okay, that's the center. No. Let's choose one of these, like right there, that one right there, okay? So boom. Okay, that one right there. See how the expansion produces a motion away from it? Okay, now let's choose down here. Let's go down for the bottom corner. Okay, I'll make the center be that. And look at how everything moves away. When I have an expanded system, any object that I choose will see itself as the center of that expansion, like that, or that one. So no matter which I choose, whichever galaxy I choose, when the whole system is expanding, each individual galaxy sees itself as the center of the expansion. Now, to try to work this through, we'll go to the famous football field universe, and a million people had questions about the football field universe. So I'll pause and turn the lights back on. Okay, so here I've drawn up a little football field universe. Now, students, people say, God, I had comments, well, I love the football field universe. So I got the comments, oh, I hated the football field universe. Okay, well, love it or hate it, the football field universe is my idea for trying to show how this system works. Okay, so here's why a football field. Well, because where else besides a football field do you have distances marked off at nice regular intervals? So on a football field, you have yards marked off, so much distance, and it's a nice regular grid, and that's all we need for this. I could have used city blocks if you prefer. So here I have the Milky Way at the 40-yard line, and then I've tried to make this as simple as possible. Galaxies A and B are at the 50-yard line and the 40 of the opposing team. And then galaxies C and D are on the 30 and the 20. And what I have is galaxy A is moving this way, away from the Milky Way, at 1 foot per minute. Galaxy C is moving that way at 1 foot per minute. And then B and D are each going that way at 2 feet per minute. So this is the type of expansion we see. Okay, this is a Hubble flow. The farther away a galaxy is from the Milky Way, the faster it's moving. Now, the point is to look at this, and we recognize here at the Milky Way that other galaxies see the same thing. Okay, why is this? Well, let's look at galaxy C. So I'm going to choose this one. Okay. From galaxy C, well, if we on the Milky Way see galaxy C moving away from us at 1 foot per minute, then what does the galaxy C look at us and see? Well, they see us moving away from them at 1 foot per minute. Okay, if you pass a car on the road and you look in your rearview mirror, you see that car falling behind you. If you're going 70 miles an hour and they're going 60 miles an hour, you see them dropping behind you at 10 miles an hour. But they look at you and they see you going ahead of them at 10 miles an hour. Okay, so galaxy C sees the Milky Way going away at 1 foot per minute. But then they see galaxy A is moving away at, well, 1 foot per minute from the Milky Way, plus 1 foot per minute that we already see it, so that has to be 2 feet per minute. And galaxy B, they would see them going at 3 feet per minute, because we, on the Milky Way, see B going at 2 feet per minute, and they're seeing us at 1, so add 1 to each one of these. Likewise, over here at D, we see D going away at 2 feet per minute, but they're already heading toward it at 1 feet per minute, so they would see the Milky Way moving away at 1 foot per minute. So galaxy C sees the exact same thing as we do. They see themselves as being at the center of the expansion, and they see that for every 10 yards, okay, that's what this is, that's 10 yards. For every 10 yards, there's 1 foot per minute of increased speed. That's the Hubble constant. So the Hubble constant would be 1 foot per minute for every 10 yards in this setup. Whether it's us or whether it's galaxy C, we all see the same thing. We see ourselves as the center of the expansion, and we see other galaxies moving away from us at a rate such that for every 10 yards they are distant from us, they're moving 1 foot per minute faster. So that if I make a graph of this, of distance versus speed or velocity, distance, 10 yards, 20 yards, 30 yards, 1 foot per minute, 2 feet per minute, 3 feet per minute. Then we on the Milky Way, we see galaxies A and C as being 10 yards away, moving at 1 foot per minute. 10 yards, 1 foot per minute. We see galaxies B and D being 20 yards away, 2 feet per minute. So we get this little graph like this, up and to the right, like Hubble found. Get people on galaxy C, they look at the Milky Way and D and see them being 10 yards away, moving 1 foot per minute. They look at galaxy A and see it being 10, 20 yards away, 2 feet per minute. And they see galaxy B out there being 10, 20, 30 yards away, 3 feet per minute. So take it up another notch. And that is a Hubble plot. Actually, recently the International Astronomical Union decided that this should be called Hubble-Lemaitre plot, because there's greater recognition of George Lemaitre. Okay, I'm going to pause this for a minute because my video is getting too long.